the German Aerospace Center this week. So I had the opportunity to also say a bit about that. It's the Deutsche Zentrum für Luft- und Raumfahrt, that's the DLR, that's where the abbreviation comes from. Let me just quickly introduce to you what the DLR does and why we are dealing with mobility, energy, and so on, while the name says just Aerospace Center. The DLR has different sections. First of all, aviation and space travel, but also since more than 40 years, energy research. As you can see here, correct, 55 institutes and still growing. In over 30 locations in Germany, and also some facilities in Canada, Spain, and so on. And next to that, the DLR is also the project management agency, which does the project management for third-party funding, and is also the German space management unit within the European Space Agency. And we're a member of the Helmholtz Association. Yeah, so now where I come from is it's the Institute of Network Energy Systems in Oldenburg, one colleague also being from there. And what we are having is this campus. We have 3 different sites with around 170 people, with lab space in the first building and more or less office space in the middle of Oldenburg for the high performance computing systems, and a different department also located in Stuttgart. The energy systems. Just to give a small framework within the DLR's research, where are we located, while other institutes focus more on the single technology sides and developing that. We are working at systems operations and sector integration for different fields of technology. So we are not dealing with developing new fuel cell systems, as my colleague is doing in the other department, other institute also located in Oldenburg, but we're trying to focus on the interaction of the systems, with our goal to have a completely renewable energy system in future, based on wind and solar power and so on. Now, what is my group doing? As Klaus already mentioned, I'm the group leader for the sector integration mobility group. And just for a short introduction, why we come to quality analysis. One focus is the fuel cell mobility and hydrogen for PEM fuel cells. And I guess you have heard that already this week, that we need a very high fuel quality or for the use of fuel cells. And we have now 3 different projects dealing with that, one of which is also the storage and underground salt caverns. I guess you have heard Tjag. Maybe he talked about the project Mobile. Our part there is analyzing how clean is the hydrogen coming into the cavern and how clean is it getting out. So we have the possibilities in our lab to simulate these cavern conditions. And also we did some lab scale purification, but the main focus is on the purity analysis down to the sub parts per billion range along the process chain whenever it comes to hydrogen usage, storage, and so on. Yeah, and then there's also, since it's mobility, there's also a part of battery electric mobility, where we try to integrate electric vehicles into buildings' energy management system. So that is the side where it comes to the integration into households, where we use vehicles as, let's say, a power source for heating electricity. And yeah, you might have heard bidirectional charging, using battery electric vehicles to store, let's say, solar energy in the vehicle and then use it when we need it. Okay. Coming to the hydrogen quality and analysis or purity, I made this slide, I think, a year ago, because what does purity or impurity in hydrogen mean actually? And I was always confused with all these numbers. You might have heard 5.0, 3.0, others say 3.9 purity, and so on. So purity is defined by the number of contaminations in hydrogen that is given in relative numbers. For percent, for example, is parts per hundreds. Typically used is parts per million. But when it comes to hydrogen, you need to even know what parts per billion or parts per trillion means. And impurities are basically non-hydrogen contaminations. This can be other gases like CO2, carbon monoxide, methane, or hydrogen sulfide, but also particle contaminations from abrasion from pipes, from lubricants, from compressors. As you might have heard, there are also ionic liquids used in compressors. And yeah, also powder from storages like metal hydrides, for example. Yeah, and here's an overview slide of what typical hydrogen quality is and for which typical applications those are used. For example, the first class here is 1.8, which the purity is better than 89%. This is currently discussed, or I think it's just recently being published. This is the quality for transportation of pure hydrogen in reused natural gas pipelines. So that is what the transport system, the reused natural gas pipelines will be able to deliver. Yeah. Then there's some other 3.0. It's a typical fuel gas. You can buy that if you want to make a hydrogen barbecue, for example. And then there's 3.7 or 3.8, which means 99.97% purity. That is the nominal hydrogen purity according to these standards that we have. That is the DIN 17124, which is basically the same as the ISO 14687. But there's a but. So the total number of contaminations of 300 or 200 ppm is allowed in total, according to this definition. But in this standard, it's a bit difficult because parts of the impurities may not be that high. For example, the last slide would be 8.4. 4 ppb sulfur components are allowed in hydrogen. So while you nominally would fulfill with 3.7 hydrogen the standard for the maximum total contaminations, it still could be non-standard if there's too much sulfur inside. Yeah. And then this 5.0 is what you typically get in bottles, maybe even 6.0, and if it's getting even higher here, you need some additional purification, membrane separation, or something else. And now 5.0 is what typically is delivered to the refueling stations in Germany. Somebody from H2 Mobility here? Well, there is a sticker on it that it says it's according to the DIN standard, and which normally would be okay. So we heard this today. Also for semiconductor production, you would need pretty high purity hydrogen. 6.0 is, I think, the best you can buy in bottles, and from there on you need, as I just said, you need already a local purification system addition. Yeah, and now what do contaminations do, and why is sulfur such a bad component? Or does everyone know already? Okay, so sulfur components are typically highly reactive, and the problem in the fuel cell is that you do have a platinum catalyst typically on the membrane. Now the hydrogen or dihydrogen sulfide would react with platinum, here indicated in the black dots on these particles, and that's permanent, which means whenever you have this reaction, you will use power in your fuel cell, and it's not recoverable. That's why the definition is so low. Then there are other contaminations, for example, carbon monoxide. They also reduce the power of the fuel cell system, but they can be recovered again by purging with hydrogen in different directions. So that's why there are different sets of allowable contamination are allowed. Now I would like to also speak a bit about impurities from hydrogen production. I'm not sure if you have heard about that already. Please somebody say no. Okay, so I know that you have heard all the pathways of hydrogen production. Still, I wanted to reproduce them here again. So there are many ways of getting from green energy like biomass, solar generation, wind, hydro or geothermal. And in the end, you will come to hydrogen. Typically, water electrolysis is used when it comes to renewable electrical energy, but there's also a pathway via concentrating solar power and high temperature heat, and using this additionally with electrical power to increase the total efficiency. Then you could also produce your hydrogen thermochemically, or with different processes like steam methane reforming or pyrolysis from biomass. All this will lead somehow to hydrogen, but with different impurities from the production process. By the way, for those of you who are interested in kind of nerdy, 3 of these colors belong to the hydrogen emission lines. This one, and the red one. And the red one, by the way, is in red RGB. It's FF00. I don't know whether this is a coincidence or it is wanted. So pure red is the hydrogen emission red. Okay, nonetheless.